Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to continue chapter 7. This session is going to be all about SN1 reactions. We're going to introduce what that is, the difference between SN1 and SN2, and then dive into a mixed problem set with a bunch of SN1, SN2, and E2 problems, because that's what we've covered so far. Next session, which will be our last session for chapter 7, will be all about E1. All right, so let's get started. The SN1 mechanism is similar to SN2 in that you get a substitution product, but it's different in other ways as well. Now, we've covered SN2, where a nucleophile replaces a leaving group in a concerted one-step mechanism. And for this, we needed a strong nucleophile in an alpha position that was primary or secondary. But we didn't talk about what happens if the alpha carbon is tertiary with a strong nucleophile, or with a tertiary alpha carbon with a weak nucleophile. Well, spoiler alert, we get SN1. And let's talk about SN1. Let's talk about a different love story. Here in the SN1 love story, the leaving group, or in other words, the halogen, actually dumps the carbon first. All right, now sometimes if the molecule is not in a good headspace after the breakup to deal with the loss, she's going to work on herself and rearrange her thoughts. And what I mean by that here is that sometimes after the loss of a leaving group, after the halogen leaves, the molecule may go through methyl or hydride rearrangement to form a more stable carbocation. Sometimes rearrangement happens with SN1 because the first step is loss of a leaving group. Now, after some time, the molecule might find herself a new lover, a new nucleophile with a good job and a 401k. All right, so here's what it looks like. Here's what this mechanism looks like. All right, first, loss of a leaving group. Halogen leaves. Halogen dumps carbon first. Okay, so the halogen leaves, loss of a leaving group, and now you have this carbocation. Sometimes here, rearrangement may happen to form a more stable carbocation, but here we already have a tertiary carbocation, which is the most stable. So no rearrangement that will happen here. All right, then after some time, all right, nucleophile will come in and attack and add itself there. All right, so the same love story, except the halogen leaves before getting dumped. Now, as for the kinetics, the rate equation actually for SN1 only depends on the concentration of the alkyl halide. So this makes it unimolecular, and that's why it's called SN1. Remember, for SN2, the rate depended on both alkyl halide concentration and nucleophile concentration, which is why it was bimolecular. Here, the kinetics only depend on the concentration of the alkyl halide. All right, so now the first step in this SN1 reaction is the loss of a leaving group. All right, and it is this step that is the rate determining step. All right, because the rate of this entire process is most profoundly affected by any changes in the rate of this step. All right, so our rate determining step in SN1 is that first step, that loss of a leaving group. Now, with unimolecular processes like SN1 and then E1, when we finally cover it, there is always going to be that possibility of rearrangement when the leaving group dips or leaves, all right? So always make sure to consider this when drawing all the potential products of a reaction. All right, so let's just dive right into it. Let's do a few practice problems, get the hang of this, all right? So here we have an SN1 reaction. All right, let's draw what this would look like. Okay, so first step is loss of a leaving group. All right, so the bromine leaves, minus bromine. All right, then what we have as a consequence is, my pen does not want to work. There we go. All right, then what we have is this carbocation right here. Now, stop, pause, ask yourself, can there potentially be a methyl or a hydride shift that would result in a more stable carbocation? Now, this is a secondary carbocation. Can we have a hydride shift that will, or a methyl shift that will result in a tertiary carbocation? The answer to that is yes. This hydrogen right here can shift over. All right, it can shift over, and then what you get is a tertiary carbocation right here. All right, fantastic. Now, this form of it before the carbocation can still react with our nucleophile. All right, and so that means we can still add alcohol there, and this would be a potential product. Okay, but then it can also create a product after the carbocation rearrangement. All right, so this can also result in a product where the alcohol actually adds in this position now. All right, so both of these are actually potentially products for this reaction that can happen. Now, an important thing to note here, all right, an important thing to note here is if you form a chiral center, all right, if you're forming a chiral center, you're going to get both enantiomers. So for this, you're going to have both enantiomers. So it's going to be actually racemic. All right, and the same goes for here. So actually what you're forming are 4 products total. All right, fantastic. Let's do one more. All right, let's do this. What happens when something like this? All right, now what we have here is loss of a leaving group is our first step for SN1. Right, so we have our chlorine. It's going to leave. All right, chlorine leaves first. And then what we form here is this. This is what happens when our halogen leaves. We have a positive charge here. It's at a primary position. That's not very stable. Can a hydride or a methyl shift happen? Absolutely. One of these methyls can shift over here. All right, and when the carbocation rearrangement happens, what we get is a tertiary carbocation. All right, now we can have a product that results from this that looks like so. All right, but this is not the major product because, of course, the product that we form from our most stable carbocation is going to be our major product. And so here, adding the alcohol here, this would be our major product. Of course, we would get a racemic mixture of this because we have a chiral center right there. All right, fantastic. Now, what we have here is just a Venn diagram very quickly just to help us compare SN1 and SN2. All right, for SN1 process, protic solvents are more suitable because they stabilize the ionic intermediate and transition states. All right, so protic solvents are more preferred with SN1. Now, SN2 is different. It prefers polar aprotic solvents. All right, because this enhances the rate of the SN2 process by raising the energy of the reaction. All right, SN1 is a two-step mechanism. SN1 is a two-step mechanism. SN2 is one-step concerted mechanism. All right, so that's another important difference to recognize between them. All right, for SN1, your first step is loss of a leaving group, and it's your rate determining step. All right, SN2 requires less substituted alpha carbons like primary and secondary. SN1 really likes the highly substituted alpha carbons. SN1 is unimolecular, SN2 is bimolecular. All right, now SN2 you get inversion of configuration. For SN1, when you get your racemic mixture, you can get retention and inversion of configuration. And actually, inversion of configuration is something that overlaps for both SN1 and SN2. They both require strong nucleophiles. They're both substitution reactions. So hopefully this Venn diagram really helps you put into perspective some of the common and some of the overlapping features of SN1 and SN2 and the things that make them really different, because that's important to be able to distinguish between the two, especially when you're trying to predict the product for a reaction and you are not told what reaction you're trying to conduct, right? You're supposed to figure it out by looking at your alkyl halide, by looking at your nucleophile and determining from there. That's why it's really important to understand the characteristics that make these similar and that make them different. All right, let's do a few more problems really quickly. All right, let's do one or two, and then the rest I'll leave to you to look at. All right, so for A, all right, we want to look at our reagent. All right, we got ethoxide. All right, we have ethoxide. Ethoxide is actually a weak base, weak nucleophile. All right, now we're going to look at the alpha carbon. It is tertiary here. Fantastic. Now, this kind of mixture, all right, tertiary alpha carbon with a weak base, weak nucleophile, all right, this actually is going to give you SN1 and E1. All right, we're just going to worry about our SN1 products because we haven't talked about E1 just yet. All right, so we're just going to try to figure out our SN1 products for this reaction. So we're going to go ahead, we're going to draw. How does it look like? All right, we're going to go ahead and we're going to draw this. All right, first step, loss of a leaving group. So goodbye bromine. It's just going to dip. All right, now what we form is a tertiary carbocation. That's probably the most stable carbocation you can have. So no rearrangement is going to happen here. All right, then our ethoxide as a whole is going to come and attack this electrophilic carbon. It's going to go ahead and add itself there. All right, and then as a last step, all right, we're going to have this come in deprotonate so that we can get our final product right here. All right, I'm just showing the whole mechanism here. All right, you're going to get the hang of this. You're going to know exactly what to do. You don't have to draw every step to know how to draw the product. All right, let's go ahead and do B now as well. Let's look at B. Okay, cool. Let's look at our reagent. We have water. All right, water is a, ooh, that's ugly. Water is a weak base, weak nucleophile. All right, and the alpha carbon there was tertiary. Okay, so once again, we're going to have a mix of SN1 and E1 here, but we're only going to draw our SN1 products, and we're going to revisit problems like this when we finally learn E1. All right, so we're going to go ahead, we're going to draw our compound. All right, here we go. And we have chlorine here. First step, loss of a leaving group, so chlorine's going to dip. All right, chlorine is going to dip. All right, that means that we have now a carbocation. It's tertiary, it's really stable, nothing's going to rearrange now. All right, then our water comes in, all right, and we're going to add not water, right, but alcohol here. All right, that's going to be the group that adds. Well, technically you add water, right, and then it gets deprotonated down to an alcohol, but we're just going to make this mechanism shorter, and this is our final product. Fantastic. I'm going to let you do C and D. Let me know if you have any questions at all or if you need help. All right, but with that being said, we're just going to move on now. All right, so far, what is our technique for these problems for our SN1, SN2, our substitution reactions, and elimination reactions, okay? We can form this technique that we can apply to any problem set to really make sure that we are approaching the problem as effectively as possible, all right? And when we have to draw all the products for certain reaction mechanisms, we might get like 3-4 products. So we want to make sure, all right, that we stay on top of it, that we're doing all the steps in order so we don't miss any of those products. Because if we don't really have a technique, it becomes really chaotic. All right, so what our technique is, what we've developed so far, and what we will continue to apply, all right, is first, what is the function of our reagent? Is it a strong nucleophile weak base? Is it a strong nucleophile strong base? Is it a weak nucleophile weak base, or is it a weak nucleophile strong base? We need to categorize it under one of these categories, right? Because this is going to help us determine what kind of reactions are going to happen here, right? That's our first step. What is the reagent? Second step, how substituted is your alpha position? All right, and based off of 1 and 2, you can figure out, are you going to have SN1? Are you going to have SN2? Are you going to have E2? Are you going to have E1? Are you going to have SN2 and E2? What kind of reactions are going to happen considering we have this alkyl halide and this nucleophile? All right, so this is really important. We have to answer those first 2 questions so then we can determine what is going to happen, and so then we can draw our products. Once we figure out what reactions are occurring, say, oh, we're going to have SN2 product and E2 product, then we can go about and draw those products. And then after we've drawn the products, we can determine what our major and minor products are. All right, So for SN2, you're usually just going to get one product. For SN1, you're going to have your inversion of configuration product, and you're going to have your retention product. By the way, your inversion of configuration is more preferred. All right, for elimination reactions, for E2, it depends on the base. If you have a bulky base, your Hoffman product is your major product. Not a bulky base, it's your Zaitsev product. That's your more preferred product. And there's also the preference of trans over cis. These are all important things to keep in mind as you draw products and then determine what is major and what is minor. And we're going to get to E1 soon enough. All right. So with that being said, all right, now we know SN1. So what that means is we got SN1 down, we got SN2 down, and we got E2 down. All right. So now we're going to do a couple of problems. All right. We're just going to do several of them and get the hang of this. It's going to be speed round problem set. All right. Consider the following reaction. Draw the major product, A and B in the boxes. All right. So we're going to have to figure out with this reagent and this alkyl halide, what's our product? And then from here with this reagent, what our product is. Fantastic. We have our alkyl halide. Here's our alpha. It's secondary. Here is a strong nucleophile, weak base. Fantastic. You know what this means? This is going to be an SN2 reaction, all right? Because we have a secondary alkyl halide, a secondary alpha carbon, and our I- is a weak base strong nucleophile, all right? This is the recipe for SN2 reaction. So that means our iodide's going to come, attack, and it's going to replace that chlorine. All right, and when it replaces that chlorine, we get inversion of configuration because that's a chiral center. So there's a wedge on the chlorine. When the iodine attacks backside, it's going to be on a dash. That's our product. Fantastic. And we'll draw roll right methyls at the end. All right, now, second thing. All right, we have sulfur. All right, we have this is our nucleophile. All right, this is also a strong base. A strong nucleophile, I'm so sorry, weak base. All right, and our product here, A, has an alpha carbon that's secondary. Again, this is a recipe for SN2. All right, so we're just going to do another SN2 reaction. And now what we get is, of course, another inversion of configuration here at the chiral center. So this dash becomes a wedge, and we add our SCH3 here, and this is our final product. Now, you're going to get really good at identifying your nucleophiles and categorizing them, right? So just make sure you study those tables we've introduced in every single video. All right, here's it for this SN1 right here. All right, make sure you master this. All right, no, memorizing just these two tables right here will allow you to do all of chapter 7 problems, okay? So make sure you commit these to memory. Make flashcards, quiz yourself. Look at those flashcards all the time, all right? Carry them, all right? Awesome. So that's how the only way we can solve these problems efficiently is if we know how to categorize our nucleophiles, all right? Let's do another problem, all right? Speed round problem. So following tertiary alkyl halide was heated in ethanol. All right, fantastic. Let's write out ethanol. All right. Now, ethanol is a weak base, weak nucleophile. All right, so we're going to write that down. This alpha carbon is tertiary. Let's also write that down. All right, this alpha carbon is also tertiary. Fantastic. So let's write that down. We have ethanol, which is a weak base, weak nucleophile, weak base and nucleophile. All right, we have an alpha carbon that's tertiary. All right, guess what? This is the recipe for SN1 and E1. Now, we haven't covered E1. Don't worry, we'll get back to these problems to do the E1 products. We're just going to focus on our SN1 products here. All right, and we're going to go ahead and we're going to try to draw this reaction right here. All right, first step of SN1, bromine's going to dip. All right, it's going to leave. And what we get as a consequence is something that looks like this. And look at that. We have a tertiary carbocation here. We do not need to worry about any kind of rearrangement here. All right, now our ethanol can come in. All right, good old ethanol. All right, attack our electrophilic carbon. All right, and now we have ethanol here. All right, then we have ethoxide in our solution as well, that's going to deprotonate that so that our final product looks like this. All right, and you're going to get enantiomers. All right, you're going to get a racemic mixture of this. All right, because that's a chiral center right there. So that means what our products look like if you want to draw the enantiomers. I mean, you could always write racemic in a free response problem, and that should be correct. But if your professor is anal about this, all right, here is both your products. All right, and now what did we say about our major product? All right, our inverted product is going to be our major product. So we started here where bromine is on a dash. All right, so the one where our nucleophile is on a wedge is our inversion product. This is going to be our major product, right? Our inversion of configuration product is going to be more preferred than our retention product. All right, that's a very important thing to keep in mind. All right, let's keep going. All right, this one says consider the following reaction. All right, we're going to draw the product for this. Fantastic. All right, now this is just a complete way of writing out something that looks just like this. O with some variable R group attached to it. All right, you know what this is. This is a strong base, strong nucleophile. You might be thrown off because they've actually drawn your R group here. All right, it's not arbitrary, but anything with an O and some R group here is of this form which you are familiar with in your table. This is a strong base, strong nucleophile. All right, this is actually tert butoxide. That's the name for this. Okay, fantastic. Now our alpha carbon here is tertiary. All right, this is the recipe for an E2 reaction and only an E2 reaction. Okay, so the way that we're going to do this then, if we're only having an E2 reaction, is we got to look at our alkyl halide and identify all the beta positions, unique beta positions. All right, there's only 2 unique beta positions. These are equivalent, right, because this is symmetric. All right, so be careful there. We have 2 unique beta positions. This one has 3 hydrogens. This one has 2 hydrogens. All right, fantastic. Let's look at the 3 hydrogen one. All right, that's just going to go through normal elimination. All right, easy peasy. That means a hydrogen's going to get abducted. You're going to form a double bond between your alpha and beta carbon, and your bromine leaves. All right, this is the product of this beta position going through E2. All right, now if we look at our other beta position with 2 hydrogens, okay, 2 hydrogens, but this is cyclic, right? So you might be thinking, oh, I know what to do with 2 hydrogens. I have to draw the cis and trans configuration, not with cyclic compounds, right? Because you can't get that, you can't be bending around small rings like this to get cis and trans. That's not very favorable or practical or correct. All right, so you're only going to draw your normal elimination product with this. Not going to worry about cis and trans. All right, so let's draw this whole out just in case somebody needs to see it. All right, here's our bromine, here's that methyl. All right, here's a hydrogen right here, right? Our nucleophile is going to come, steal this hydrogen. It's going to form a double bond right here, and our halogen will leave, which means our product is going to look like this. All right, so now we have our 2 products. These are our 2 products. Let's write some information about them. This is di-substituted. This is tri-substituted. Now, in order to say what our major product is, we're going to have to look at our base. All right, our base is tert butoxide. This is a very bulky base. All right, now if you have a bulky base, your preferred product is your Hoffman product. What is a Hoffman product? It's your least substituted product. All right, that means our di, which is our least substituted product here, is our major product. All right, it all depends on what our base is. Bulky base prefers least substituted product, not bulky base prefers more substituted product. Fantastic. Now, let's look at this. We need to figure out which one of these is an actual product for this reaction. All right, we have here our alpha is secondary. All right, it's secondary, but our nucleophile here this is a fancy way of saying R. This is the R group, OH. This is a weak base, weak nucleophile. All right, this weak base, weak nucleophile with a secondary alpha is going to result in an SN1. It's going to result in an SN1 and E1 reaction. Now, we're going to have to ignore E1. We haven't talked about it yet. All right, so we're going to just at least try to draw our SN1 reactions. Okay, so let's start. First step of an SN1 is the loss of a leaving group. So our bromine is going to dip, minus bromine. What we get here is a secondary carbocation. Now, we can have a hydride shift over here to also get a tertiary carbocation. All right, so when this hydrogen moves over here, now we have this tertiary carbocation. Now, both of these can result in products. All right, your ROH group can react over here at the secondary position to give us a product that looks like this. All right, minus the hydrogen whenever you're drawing this, right? OCH2, CH3. And it can also react at the tertiary location to give you this product right here. All right, now, is that present here? Is that are either one of these demonstrated here? Perfect. This is A and B. We have done this correctly. All right, it's telling us these three things are our products from this reaction. And look at that, we obtained A, this is A, and we obtained B. Fantastic. Now, if we knew how to do E1, we would obtain C. We're not going to worry about that, right? We're going to get to E1, and we're going to come back to some of these problems and do the E1 portions of them, right? For now, we're just going to ignore it because we don't have that knowledge just yet. All right, next problem. All right, lots of problems here. Rank the following alkenes in order of stability. Assign E, Z nomenclature for compounds B and D. Awesome. So we're just going to look at each one. We're going to look at the double bond. We're going to say mono, di, tri, substituted, and then we're going to assign E and Z if possible. All right, A is just mono substituted, and there's no cis or chance for us to determine if it's E or Z. All right, let's look at B. All right, if we divide the double bond in half, we have our two biggest groups on opposite sides. All right, so that's trans, or in other words, the fancy notation is E, and it's tri-substituted. All right, now let's look at C. It's only di-substituted. All right, and we can't do cis or trans here. And here, if we divide this in half, all right, we have our two biggest groups on opposite sides, and it's tetra-substituted, and it's trans, so E. All right, fantastic. Now, if we want to order these in the as most stable to least stable, obviously our tetra substituted double bond that's in a trans conformation is obviously going to be our most stable alkene here, followed by the tri substituted trans conformation. All right, then followed by di, and last but not least mono. All right, so our most stable alkene is our trans tetra substituted alkene. All right, most stable alkene and least stable alkene. Fantastic. All right, let's just keep going. We're making good progress here. Which of the following compound contains a Z alkane? All right, you could think about this as cis. All right, so if you divide the double bond in half, you're going to have your two biggest group on the same side of the double bond, on the same side. All right, that's what Z refers to. Now, if we divide this by half, all right, this doesn't help us. There's not really a assignment here. If we divide this by half, we have our two biggest groups in trans, not what we're looking for. All right, again, if we divide this here, not useful. All right, two biggest groups on opposite sides, trans. But if we look at this final one, we have our two biggest groups on the same side. So this is going to be our answer. All right, so just to recap, for the EZ naming protocol, for each carbon of the pi bond in question, rank the item directly attached as 1, 2, 3, 4 based higher on atomic number and higher priority, and ask yourself where 1 and 2 are relative to each other. All right, if they're on the same side, if your two biggest groups are on the same side, Z. If they are directly opposite sides, E. All right, just to make that clear. All right, let's keep going. More practice problems. Rank the following molecules in order of reactivity towards a bimolecular elimination or an E2 reaction. Fantastic. So reactivity for an elimination reaction is based on how substituted the alpha carbon is. All right, the reaction E2 is favored in highly substituted reactions, like tertiary is extremely favorable. Then it decreases the less substituted it is, because then other things can be more favored. And just in general, for E2 reactions, the least substituted the alpha carbon is, the least reactive it is. All right, so this alpha carbon is primary, this alpha carbon is secondary, and this alpha carbon is tertiary. All right, the order of reactivity is your tertiary. Your most substituted alpha carbon is going to be most reactive. All right, so C is the most reactive. C is most reactive, then tertiary, then secondary, which is B, that's second reactive, and then A is your least reactive. So in order of most reactive, we give C order 1 because it's the most reactive. We give B 2 because it's secondary. And then A, for primary substituted alpha carbon, this is not reactive at all. Not very reactive towards E2 reaction. All right, so keep that in mind. Now, here we want to rank the following alkenes again. Lots of practice with this in order of stability. Okay, so again, here we want to label these. How substituted are they? Are they E or Z? And then we'll figure out. So A here, oh, my pen is, okay, A here is di-substituted and it's trans, all right? B here is also di-substituted, but it's cis. C is mono-substituted, lame. And D is tri-substituted, all right? And it's also trans, okay? Or E. I guess we should be using the proper. This is E, this is Z, and this is E. All right, most substituted is going to be that substituted alkene that is in configuration E. So this is the most stable. So D gets 1 because it's the most stable. Next, what's the next most stable? It's this di substituted in E. All right, so A is the next most stable. So we give it a 2. All right, then next up is the di-Z configuration. So B gets 3. It's the third most stable. And C, this mono, it's the least stable of the alkene. So it gets a ranking of 4. All right, so our answer is A. Fantastic. All right, now let's do 10. Not that these are numbered weirdly because I've just taken them from old exams of mine. All right, anyways, consider the following substitution reaction. All right, it's a substitution reaction. All right, we have our chlorine here, strong nucleophile, weak base. Okay, and our alpha carbon here is tertiary. All right, so strong nucleophile, weak base, and it's tertiary. Perfect recipe for SN1 reaction. All right, and we were already told it's a substitution reaction, but now we know which one. All right, so let's figure this out. All right, let's draw this really quickly. All right, just so we know what it looks like when it happens. And then we'll read through the options and see which of the statements is not true. All right, so let's draw this really quickly. Bromine leaves first. All right, bromine leaves first, and we form this tertiary carbocation. Beautiful, no rearrangement here. And then we have our chlorine come in and attack the tertiary carbocation place, and we add chlorine here. All right, and we get a racemic mixture of this, so we get enantiomers. All right, perfect. Let's read these and see which one is not true. The rate of the reaction is not sensitive to the concentration of nucleophile. This is true. SN1 is only the rate only depends on the concentration of the alkyl halide. So this is a true statement. It doesn't matter about the concentration of the nucleophile. The reaction is first order in A. This is correct, right? Because remember, our rate equation only depends on one thing. So rate first order. The reaction generates an intermediate. Yes, of course it does. Remember, loss of a leaving group happens first, and we generate an intermediate. All right. The reaction is sensitive to the stability of the intermediate always, right? Because depending on the intermediate, things might rearrange. Rearrangements might happen. So SN1 is indeed sensitive to the stability of an intermediate. This is also true. E says the major product is produced as a single enantiomer. No, we get a racemic mixture. So this statement is incorrect. All right. There's a chiral center. SN1 gives inversion and retention configuration. Our products are enantiomers, a pair of enantiomers. Fantastic. Let's keep going, guys. There's a lot of problems here. I think I overestimated how long this might take. Anyways, all right, we have our alpha carbon. It's secondary. We have strong nucleophile, weak base. All right, this is an SN2 reaction. All right, so this is going to replace the iodine, and it's going to do inversion of configuration. So it's not going to be on a dash, it's going to be on a wedge. And so our product is D. All right, since we know SH3, all right, this is the key, knowing these nucleophiles really well, right? SH3 is a strong nucleophile, weak base. We have our alpha carbon, it's secondary. Easy, it attacks, this leaves, and it goes on the opposite of that dash, so on a wedge, because SN2 does inversion of configuration. All right, easy peasy. All right, next we have, which of the following is the major elimination product of the reaction below? All right, which of the following is the major elimination product of the reaction below? All right, so let's make some notes. What is our reagent? Well, our reagent is tert butoxide. All right, or in other words, it's commonly seen as OR. And this is a strong base, strong nucleophile. Our alpha carbon here is secondary. So what's going to happen here is we're going to get SN2 and E2, where our E2 products are our major products over our SN2. Okay, so here the problem asks for our elimination product, so we're not going to worry about SN2 because the problem asks us not to. All right, so which of the following is the major product? So let's draw. Let's get into E2. All right, first, how many unique beta positions? All right, let's figure that out. Let's look at our molecule. All right, we have one beta position here and one beta position here. All right, we're going to call this one A. We're going to call this one B. All right, let's look at A. That beta position has 3 hydrogens, normal elimination with nothing to worry about. All right, so we're going to go ahead and we're going to draw what that looks like. That means that we get a double bond right here between the alpha and beta position. And of course, our halogen leaves. Fantastic. All right, now let's do B. How many hydrogens does that position have? It has 2 hydrogens. That means we need to think stereoselective. All right, and that means we're going to get cis and trans here. We need to draw the cis and trans product. All right, so let's go ahead and do that. All right, let's first draw our trans product. All right, that double bond forms there between the alpha and beta position. And guess what? The 2 biggest groups are on opposite sides. And then let's draw our cis product. This is our cis product. All right, now let's label these. This is di-substituted and this is di-substituted, but this is trans and this is cis or Z, right? Our correct assignments. Now this product was mono-substituted. What is our major product? Well, we have to go back to our base. This is a bulky base. That means our least substituted product is our major product. So that means our mono substituted product is our major product, and that will be answer choice B. All right. On to the next problem. This one says, what is the major product of the following reaction? Okay. We have a alkyl halide that is secondary. The alpha carbon is secondary. Oh, and look at that, CN minus. This is strong nucleophile, weak base. All right, this gives us SN2. All right, so we're going to be replacing that bromine with CN. All right, but remember, inversion of configuration for SN2 when there's a chiral center. So our CN should not be on a wedge like bromine. It should be on a dash. So our actual product is E. All right, fantastic. Next problem, Next problem. All right. Cool. We have, this is going to be an intramolecular reaction, all right? Here is our nucleophile, which, by the way, is a strong nucleophile, strong base. All right, our alpha carbon here, all right, it's primary. All right, so what we're going to get here is SN2 and E2, but SN2 is the major product over E2. All right, and we want to draw here our major product. All right, so that's what we're going to do. What happens here, all right, is this lone pair in alcohol, in the alcohol group, is going to attack that alpha carbon right there. What we form is a ring around the oxygen. So however many carbons we have here, 1, 2, 3, 4, 5 carbons. All right, we're going to have 5 carbons, and the oxygen is going to be part of the ring because it's attacking that carbon and closing the ring. All right, so we're going to have 1, 2, 3, 4, 5 carbons, and the oxygen is going to be right there. Now, it's going to keep the wedge and the methyl group right here when that happens. All right, so our product here is going to be A. All right, fantastic. All right, let's do 17 now. All right, we're nearing the end of our mixed problem set. Okay, what we have here is an alkyl. What we have here actually is an SN1 reaction. All right, what's going to occur, but instead of an alkyl halide, we're actually dealing with the alcohol. And we're actually going to talk about this in more details in a little bit, but we're going to do the same thing here. All right, it's still going to be a substitution reaction, but instead of an alkyl halide, we have an alcohol group, which is also going to act as a leaving group. Okay, so what happens is the alcohol will take the hydrogen from the bromine, all right, so that it can form water because it can't leave as an alcohol. All right, so after it forms this water, then it can leave. And then what we get is something that looks like this, a secondary carbocation. All right, this is going to form a product on its own. All right, this is going to form a product on its own where the bromine will attach there. All right, but then a carbocation rearrangement can also happen where a hydride shift happens, and what you get is actually a tertiary carbocation after that happens. And then you can also have your bromine attack there and get a different product right here. All right, fantastic. All right, and so those are your two products. Your major product is going to be the one that is formed from the tertiary carbocation. So this one is your major product, and that will be D right here. Awesome. All right, oops. Sorry, we're on our last problem here. I forgot to erase the answer so we can work through it together, but we can just talk about this, all right? Again, this is going to be an SN1 reaction, but we're dealing with alcohols here instead of alkyl halides. This is okay. We're going to get into more details about this later on. My mistake for including it in this problem set, but we'll talk about it anyways, okay? So you have an alcohol group. Just like alkyl halides, this alcohol group can protonate to form water and then leave, and then you can do the same thing that you would do in a normal SN1 reaction. So the alcohol will steal the hydrogen from this, all right, and then it's going to form water there, and you can see the mechanism right here. All right, now this water can leave on its own, and you have a tertiary carbocation, and then the bromine can attack here and give you the product. And of course, you're going to get both enantiomers as your product. Do not worry, we're going to get into more details. We've been talking about alkyl halides this whole time. In our last video, this next video after this, we're going to be talking about having alcohol groups that you can still do the same substitution and elimination reactions with some extra steps sometimes. All right, with that, this is the end of our mixed problem set. I hope this was helpful. Let me know if you have any questions at all. Other than that, good luck and happy studying.